Today we'll talk inverses of trig functions. We've already kind of done this. If I asked you, well, what kind of theta value gives you a x value of root 2 over 2, you'd go over to your unit circle and say, well, pi over 4 gives me 1. And then you'll notice also at 7 pi over 4, I have another x value of that. Now in geometry, to solve for theta, we basically took the inverse of both sides. Now the inverse is also sometimes referred to as the arc. So this is inverse cosine and this is arc cosine. They're actually the same two things. But we get all these values from our unit circle. Now, if I ask you again, where do I have a 1 over y value equaling to 2, then I'm looking for y values of a half. And you'll notice I have one at pi over 6. And I have another at 5 pi over 6. And in theory, anytime I add 2 pi to one of those, I also have theta values that are equivalent to the inverse cosine of 2. So if they're just asking me to find theta, I've got infinitely many answers. Likewise, if I want to find the inverse tangent of root 3 over 2, I'm looking for a y value of root 3 over 2 over a half, which gives me root 3. All right, so this is my y and this is my x. And they either both have to be negative or both positive. So that's at pi over 3. And you'll notice right here, that has the same value and it's pi away, so every time I go pi n, multiples of that, I also get a value. Okay, so we're asking questions that have infinitely many answers in a case like this. So you'll notice in the inverse sine graph where I take the x and y, switch them, and solve for y, you'll notice here is a graph of the sine function. And here is the graph of its inverse where I switch the x and the y coordinates. And you'll notice it doesn't pass a vertical line test. So over on the right here, I have an actual inverse sine graph that does pass a vertical line test. And you'll notice that it floats between pi over 2 and negative pi over 2. So my output answers for a given sine graph go from negative pi over 2 to pi over 2. And this is now going to be the implied answer if they ask for an inverse and don't state over which bounds. You'll notice the domain in this case goes from negative 1 to 1. But this is where my answers are going to come from. Now, if I do the same for the cosine graph, it will also repeat itself. But in this case, it repeats itself in a different interval. And you'll notice that interval goes from 0 here to pi. These are the output values for inverse cosine, over again that interval of negative 1 to 1. Tangent's a little bit different story. Again, here's the graph of tangent, and then in the blue is the inverse, and here is the inverse function. Again, all isolated by itself. You'll notice its answers fluctuate between negative pi over 2 and pi over 2. And then the domain in this case ends up being all reals.
So in taking a look at the cotangent function, you'll see that we have roughly 4 periods of cotangent represented here, and it decreases as cotangent should. If we switch the x and the y and solve for y, here's our inverse cotangent graph, and you'll see that it really does decrease as we go through the values of theta. We go from 8 to negative 8 as we grow from 0 to theta. So this is defined from 0 to pi, because if we were to graph another period of this somewhere along here, it would stack on top of each other and not pass a vertical line test. So again, this is defined from theta going from 0 to pi. Okay, or its inverse is defined, theta to 0 to pi. Now, as a cheat sheet, what I usually do is I draw a couple of pictures. I have three functions whose inverse can only be derived between negative pi over 2 and pi over 2. And I have three other functions whose inverses can only be stated between 0 and pi. So once again, sine, cosecant, tangent can only exist, their inverses that is, between pi over 2 and negative pi over 2. And cosine, secant, and cotangent, their inverses, can only be expressed in terms of values between 0 and pi.
So when they say find the exact value of the expressions, I know we did some of these earlier in the day, but we didn't have this new information. So now what this inverse means is that I may only give you answers between this negative pi over 2 and this pi over 2. So where do I have a y value of root 3 over 2 between negative pi over 2 and pi over 2? Well, that's at basically 60 degrees, right? Or up at pi over 3. Likewise, where do I have a negative tangent value? And that again is between pi over 2 and negative pi over 2. That's down here somewhere, all right? And that's going to be at negative pi over 4. Again, we want to find the exact value of the expressions. Now, this is a totally different setup. You'll notice they're asking you for a sine of pi over 13 of the negative type, and I have no idea where that is. All right, I can't tell you what the y value of this is going to be, but I do know that if I were to draw my graph, it's somewhere over here, and it says, finally, in the second part of the parentheses, what angle gives me that y value of this statement? Well, that angle is just negative pi over 13 in this case. And that seems kind of, intuitive. But when I come over to this problem, it's going to be a little bit different. And here's why. They're asking me to find the tangent of 6 pi over 7, which is somewhere over here. I can't tell you the y over x value of that because it's not a unit circle problem. But they want to know what angle gives me that value. Well, I know there's a reference angle right here of pi over 7. All right, and the problem is I can't state, well, your answer is 6 pi over 7 because I have this implied inverse tangent. I can only get answers from this part of the circle, which goes from pi over 2 to negative pi over 2. Well, that reference angle of pi over 7 is going to yield the same y over x value as 6 pi over 7 does over here. Therefore, we state our answer is going to be negative pi over 7. Do a couple more.
And here we have a cotangent function. So we know, since we're talking about cotangents, we're going to be talking about inverses that lie between 0 and pi over 2. If I take a look at 10 pi over 7, I look at a circle and I say 10 pi over 7 exists somewhere in the third quadrant. I have this reference angle, theta, that is here. And within the 0 to pi range, I know that In the third quadrant, I have a positive cotangent, so I will have a positive cotangent in the first quadrant. So I'm going to need this angle. I know that this reference angle here is 3 pi over 10, or 3 pi over 7, I'm sorry. So this angle in the first quadrant of 3 pi over 7 is going to have the same x over y value as 10 pi over 7. And my answer ends up being 3 pi over 7. Now in this case, I note that I'm talking about cosine. So again, since I'm talking cosine, somewhere between 0 and pi. Don't know what the cosine of 41 pi over 24 is. But I know I can rewrite that just to make my life a little bit easier as the inverse cosine of the cosine of, I'm just going to go 1 and 17 over 24 pi's. All right, so now I have a little better idea of where that is. 17 over 24 is more than a half. So that's going to put me somewhere in the fourth quadrant here. And I know if this is 17 pi over 24, then I know to get to 24 over 24, I'm going to need 7 more pi's over 24. So that's this reference angle. Now I have to find where the cosine value in this region is going to be the same as the cosine value of this reference angle. Cosine here is positive, which means I know again I'm in the first quadrant. And this will also be 7 pi over 24. That's the answer, 7 pi over 24.
So we switch modes in this problem because we have an inverse on the interior of this function, and then we're asked to, first of all, find the angle and then take the cosecant of that. Now the problem is, I know the angle's in the first quadrant, not a big deal, but I'm asked to find where or what angle gives me an x value of 5/13, and I have no idea because it's not one of our nice, pretty angles on our unit circle. But I do know this. I know the cosine is equal to the adjacent, or the x value in this case, over the hypotenuse, which is the radius. So I can say, well, hey, I've got something like this. I've got an angle theta where an x value is 5 and a radius value is 13. And because this is a Pythagorean triple, I can say that my y value is 12. And all of a sudden, if I don't know this angle, but I know that that angle is associated with this triangle, then I can find the cosecant of that theta value in this given triangle, because I know the cosecant is basically the r value over the y value. So for this particular triangle, my r is 13 and my y value is 12, and I have the answer solved. A similar problem, except now we have an angle in the third quadrant, which means that if I draw a triangle down here and put an angle, I know both my x and my y's are negative. So in this case, it's an inverse of a tangent. I have no idea what angle gives me that. But I do know that the tangent is equal to the y over the x value. So this would have to be a 15, and this would have to be an 8. And again, this is a nice, clean Pythagorean triple, 8, 15, 17. And I'm asked to find the cosine of an angle. And cosine is the x over the r value. So again, for this particular triangle, since these are both negative as we talked about before, my x value is negative 15, my r value is 17, and I have my solution. Let's do one more. Similar to this, it says my cosine is somewhere such that its x value is greater than 0. Well, that means my x value is positive, which means I have to be in one of these two quadrants. Given that, I'm asked to find the inverse sine of 3/5, which means my y value is a positive and my r value is always positive. So that means my angle is somewhere in the first quadrant. So I'll draw a first quadrant triangle. I'll put a 3 and a 5 here, which means my x value is 4. And I'm asked to find the cotangent of whatever that theta value is. So cotangent is just the x value, or 4 in this case, over the y value of 3. Going a little more abstract, it tells me I need to find the inverse cosine of 5x, or 5 times an angle. Let's make, instead of x, we'll call that theta. And it says I'm in the first quadrant, so I'll draw again a first quadrant triangle. And there's actually a ratio here, 5 theta is equal to 5 theta over 1. And if I'm talking about a cosine value, that's the x over the r value. So my r is 1 in this case, my x is 5 theta. And then I can find my y value by taking and doing a Pythagorean. I have 1 equals 5 theta squared plus, I'll just call it y squared. So this is 1 minus 25 theta squared is equal to y squared. And I want that y value, so just 1 minus 25 theta squared, square rooted, and we can say this could be a plus or a minus, but since it's in the first quadrant, I know it's strictly positive. So I have 1 minus 25 theta squared for that value. And that's all there is for today. Until next